Right, welcome back everyone. Now this is another level for the maths problems related to summation of series. All right, let's take a look at this. Now before we start with solving this problem here, there are a few identities that we need to develop here. All right, so the identities that I'm going to develop for you to see and for you to use to solve this problem here. Right. So in this case, this form basically looks something like this form here. Okay, now the format looks something like this. This is like sine A sine B form divided by, for instance, cos C plus cos D format. So here I'm going to develop a formula for us to use for this and for this. Right. Anyway, both of these formulas are indirectly found in this data booklet here, in the data booklet MF19. Right. But I'm going to show it to you how we can deduce it manually and then use it in exam. All right. Now, if you deduce it and use it in exam, well, the marks will be more than 2 then. All right. So let's take a look at how to work with this shortly. So I'm going to erase this. I'm going to show you how to derive both of these um, trigonometric identity so that we can use it directly. Right? Stay tuned. Right, now the first part, we're going to consider the numerator. So the numerator is given by such. So here I'm going to let A be n minus 2, sorry, n minus half, and then B equal to a 1 here. So it's easier to refer to. Okay, now I'm going to use one of the trigonometry compound identity for cosine. So I'm going to use cosine A minus B, for instance, is equal to cos A cos B plus sine A sine B. Okay, this one you can get it from the data booklet. And then that will be our first equation here. Now, the second one is the same identity, but instead of using minus, we're going to use a plus here. Okay, so that will be cos A cos B, subtract instead. Right, now that will be our second equation. So here we're going to solve this simultaneously so that we can get a form of the products between these both sign. So you can see that from here. We can take 1 subtract 2. So if we take 1 subtract 2, we will have this as a 2 sine A sine B. Okay, so if you subtract this, it will be 2 sine A, 2 sine B. All right. Now, there's a 2 already. So since there's a 2, I might as well consider this then. It will be much more direct in this case. So therefore, the 2 sine A sine B is actually equivalent to cos A minus B. Subtract off with cos A plus B. Okay, so there you go. This is our identity that we can use now. Since A is equal to this, now I'm going to substitute this value inside here. Therefore, we can deduce that sine n minus half sine sine 1 in this case must be the same as cos A plus B. So your A plus B is this n minus half minus 1. Is that correct? Minus 1. Did I get it correct? Just let me check. Cos A plus cos B. So the A is this. The B is... Oh, all right. I think this one's supposed to be a half. Sorry. Let me correct that. I think based on the question itself is half. All right. Now I accidentally write this wrongly, so that's actually a half. So we are considering 2 multiplied with sine n minus half, sine half here, where the b is a half. So therefore, I'm going to minus by half here. So that's our b. Subtract off with cos a plus the half here. Right. So from here, you can see that this can be reduced to n minus 1 now. Subtract off with cos n. So therefore, this expression here can be simplified into this form here, right? So I hope that is clear. Now the second part. Now the second part, we are going to consider consider this one here. So for the second part, we're going to consider what am I supposed to consider here? So we're going to consider the cos 2n minus 1 plus cos 1 here. So this is the denominator. All right. Now using the same identity here, all right, using the same identity, we notice that this is actually cos A plus cos B actually. Cos A plus cos B. All right. So now we're going to consider this, and then I'm going to work it out separately then, right? Because it's quite long here. All right. So maybe I'll just stop at this point. I'm going to erase all this. All right. Now I hope the first part you are clear. This is the result that we obtained. All right. Now I'm going to analyze and consider the denominator, and then uses the same identity here to simplify the expression. All right, stay tuned. All right, now next we're going to consider the denominator, right, which is given by this expression here. Well, let c equal to 2n minus 1, d is equal to 1 here. By applying the same compound identity instead of using a and b, so that we don't um, conflict with the previous numbers there. Right. So from here we are going to solve this simultaneous equation. We are going to have, since we are using a additional rule here, we will use 1 plus 2 here. Okay, that would yield cos s plus c plus d. And then if you sum up these two equations here, we will end up with 2 cos c cos d here. All right. Okay, but anyway, if you compare this form and this form here, all right, now we notice that there's only one term here, so we let our c equal to this, d equal to this, right? Okay, so now you may find it a bit different here. So what we can do is instead of using this directly, we can rewrite that. So 2n minus 1 plus cos 1 can be written as, so in this case we can write as, if you want to write in this format here, for instance, you can see that your c is actually indirectly is like 2n, and then your d is actually a 1 here. Right? If you actually do that, right, then this one would not really tally then. Okay, so one way to go about this is, okay, yeah, I think we do it this way. It'll be much more easier here. So now, of course, in the exam, we are not going to derive this. In order to do this, we will let, in this case, we'll let p, okay, because this is just c alone. Let me see. Okay, let's c and d. Okay, that's cool. So instead, we are going to let p equal to c minus d, for instance, whereby the q would be equal to c plus d then. All right. So from here, I'm going to create another simultaneous equation here, number 3. This is number 4 here. And then by solving this, you will find out that the c is Okay, so the C itself is basically half a P plus Q, and then whereby the D itself is half P minus Q, P minus Q then, right? Okay, all right, now okay, so this is what we have at this point of time. So instead of writing that as C minus D instead, so we can actually convert equations number 2.5 for instance. So we can actually convert these equations 2.5 into this. So we can convert this into this. Now you can see that that become cos, is it cos P? Yeah, correct. Cos P plus cos Q is equal to 2 cos the C instead now will become half P plus Q. The D would instead become half P minus Q. Right. So comparing this one with this one, it'll be much more easier to work with. Right now, using this analogy here, you can see that cos 2n minus 1 here, which is the same as this now, plus cos 1. Okay, that would be the same as 2 cos half. So it's actually P plus Q. So this is P plus Q here. So if you add them up, it's actually 2n. And then cos P minus Q. So P minus Q is actually half 2n minus 2 here. And if you deduce this and simplify that, it will become cos n minus 1. Alright, so there you have it. We managed to simplify this into a more manageable form. Right, we are going to refer to our first result just now, the sine. So I'm going to write down here sine n minus half, sine half here is equal to the result that we have deduced just now is n minus 1 minus cosine n here. So this is the numerator, this is the denominator. Now we're going to simplify the whole expression shortly. All right, here we go. Let's refer back to the questions one more time. And now these are the results that we have derived from our previous trigonometry compound angle identity. So this is the one that we have for our numerator. And then this is our denominator's result. Of course, this is 2 times of this. All right. Now, therefore, from here, I can write down un now is actually 2 times 2 sine n minus half sine half here. All right, so you can see that. And then the whole thing divided by the denominator plus cos 1. And then this whole thing can be simplified using the right hand expression here. So we can write it down as divided by, okay, so we have here cos n. All right, there you have it. And then right after that, we can simplify the 2, of course, and then divide and conquer this expression to produce its partial fraction. So therefore, this will become something like this now. Okay, so you can see that from here, we can reduce this. Therefore, Okay, therefore we can simplify into this form, which is as required. Okay, now of course in this case I do need to make remark that cos n is not equal to 0, and then at the same time when I reduce this, n minus 1 should not be equal to 0 there. Right. And then there you have it. We have managed to prove the first identity. All right. We're going to use the identity proven here to obtain the summations of this series. Right. So once we have proven the identity for the sequence here, we are going to make use of this result using methods of differences to find the summations of this series. All right. So therefore, I'm going to write that down here. Un. So the sum of this series is given by. We're going to sum it up until n term here. So that is basically the same as this, because un is given by this. So I'm going to write that down as this. Okay, and then maybe it's best if we put a bracket across here. Then you're clearer. All right. Okay. Now, what this actually mean? We still need to elaborate, sort of give more detail to these summations, because this is a simplified form here. Now, if we try to give more detail here, okay, maybe I'll try to write down at the side here. It'll be easier. That basically means 1 over cosine 1 minus cos 0 here. Okay, now that will be our first term. And then we're going to sum up with 1 over when n is equal to 2. Okay, so when n is equal to 2, that will be 2 minus cosine 1. Right now, that will be the second term. And then after that, we're going to continue on with the third term. So you can see that this one will be 3 minus cosine 2. And then, of course, we're going to continue on with these summations. And then, okay, I think I put it down here easier. So we're going to continue its summation here until we get something like this. So I'm going to show a few last term from the back. We will start off from n minus 1, then it'll be easier, I think. So n minus 1 will be easier to gauge here. So we will let n equal to n minus 1. So therefore, we have the second last term here. That will be cos n minus 2, of course. All right, so we're going to sum them up. Okay, and then after that, we have the n term up to n. Okay, now this is my mistake. One more time, I forgot to change the label for the number of summations that I'm trying to sum up here. This one's supposed to be n minus 1. This one will be n minus 2. And then when we reach the last term, this is the expressions that I'm getting. There will be n minus 1 there. All right, and then there you go. And then you notice that from here, we sort of can eliminate this term and this term here. Okay, you will notice that this one can also be reduced with the previous term, and then at the same time, we can reduce this. And at the same time, we can also reduce this with the previous term here. Now, by doing so, um, yeah, don't forget we can also reduce oops, I think I reduced the wrong, oh yeah, correct. So we can also reduce the cos 2 with this one here. So all along we have actually eliminated every single intermediate expressions that we have here, except those that I did not eliminate, like this one and this one. So therefore I can simplify this whole entire summations to I only left with this and this, so therefore I can write this down as cos n minus of cos 0. Cos 0 is actually a 1. So therefore, doesn't matter whether this is degree mod or radian. So that is basically a 1. And then therefore, we managed to deduce an expressions to represent the summations of this series here. Right? So I hope that is clear. I'm going to move on to the last section shortly. Right, let's look at the last sections for this question here. We need to explain why the infinite series u1 plus u2 plus u3 until infinity does not converge there, right? So now u1 plus u2 plus u3 and so on and so forth can be written in the summation form as un. Okay, hold on. Okay, can be written in summation form as using limits here. So as n approach infinity here, so I can use the summation here. So n is equal to 1 until n un here. So that is basically representing the summation of all these sequences. And then we know that we have obtained the expression for this summation series. So therefore, we have this approach infinity, and then the summations of this series is given by cos n here minus 1. All right. Now we know that cos n is a periodic. Okay, it's a periodic function. So cos n is a periodic functions. Therefore, it always fluctuates between 1 and -1, right? So maybe it's best if I show you that. Okay, just let me get my GeoGebra here. Okay, let's move it over here. It will be easier to see. Okay, so let me try to plot the graph 1 over cos x here. Now you can see that this graph is actually a periodic graph, periodic function in this case. So it's always fluctuating between anything more than 1 and then anything less than -1. Now, because the value is always fluctuating here, so therefore the summation series will not converge to a specific value here, right? So that is the main reason. I'm going to write down here. Since cos n is a periodic functions, therefore um, there will not be any limits here. Okay, so therefore this is a periodic function also. And then because it's a periodic function, it fluctuates up and down. Therefore, we can say that u1 plus u2 plus u3. So here the limit n approach infinity 1 over cosine n minus 1 does not exist. So we are saying that the limit for this does not exist. Therefore, does here maybe I'll write down here. Therefore, u1 plus u2 plus u3. So this summation series does not converge. Alright, so I hope that's clear to you. Until I see you again, thank you very much for watching.